Děkuji za úvod. Děkuji panu děkanovi za to, že hezky načasoval předání té ceny. Je to hezký začátek a spadla ze mě tréma. A taky děkuji vlastně komisi a předsedovi komise za opravdu překvapivě náročnou práci, kterou udělali. Oni opravdu studovali všechny detaily té mé aplikace. Mě to překvapilo a jsem rád, že jsme každý řádek toho ověřili a je to snad v pořádku. Já jsem kolegům slíbil, že budu mluvit v angličtině, protože někteří z nich se chtějí dívat online. Tak let me switch to English. Today I'll be talking 20 minutes, hopefully, about some research results, or mainly my research results in the past 10 years. Of course, 20 minutes is not enough, so I try to select some highlights. Then I will spend probably less than 10 minutes showing you some or summarizing some results of let's say, my contribution to the university and to all the projects and all the scientific metrics, I would say. As you can see on the video here, we are working like towards designing fully autonomous aerial robots and teams of robots. So all of the vehicles you can see are fully autonomous robots with onboard perception, onboard computational power, onboard AI, so we don't have any safety pilots, usually almost any communication. And as you could see, we are focused on deploying of robots in the real-world conditions. So even we don't have any flying arena, we are probably the only such a big research group in aerial robotics without any arena. It's purposely because I don't want to allow students to be in such an environment and they have to directly go to the real nature. I have to, of course, highlight that all of these results wouldn't happen without support of my research group. Currently, we have around 45 employees, plus 40, let's say, or plus even more master and bachelor students and many autonomous robots. We are proud of some successful events, competitions we won. Again, it was thanks to the fact that we are flying mainly in real-world conditions, because all of these competitions were pushing research in this area towards real-world applications in real-world conditions. I will tell you some details. Now I selected some key research streams of let's say my group, towards designing multi-robot systems to be deployed in real-world scenarios. In fact, I found or selected these streams based on my experience in this field robotics. The first one is agile flying. Currently, the aerial robots that are really flying close to obstacles and in real-world environment are pretty slow. And this kind of blocks us to deploy these methods of flying, teams of flying robots in real-world applications. This is why I hired Robert Piednička as my postdoc, and he proposed some methods towards agile single robot platforms, let's say. He achieved to get a Junior Star project, and we plan to, at the end of this project, to integrate these results into swarming research I'm working on. A similar story happened with Tomáš Báča, another my postdoc. We were together working on deploying of teams of robots in large areas to be able to map really large areas in different environment, to be able to do transitions from indoor to outdoor, from forest to lakes, whatever. he also managed to get Gotcha Junior Star project starting, in fact, this month. So again, the plan is to integrate these results into multi-robot systems. The third postdoc, Wojciech Wonasek, is working on motion planning, not only for drones, but we are using his results again to advance the techniques of multi-robot systems, I would say. So I will be not talking about these three streams because they are led mainly by my postdocs. And I will be focused on the projects that I am a principal investigator. It is mainly the swarming and formations of micro-aerial vehicles. It was supported by already 4 Gotcha projects, in fact, in a row I'm getting. And the long-term motivation of this research is swarming in GNSS denied environment and without communication, simply because during the deployment of the robots in conditions like you can see here, like a forest or really in the nature, we had a lot of troubles with GPS, with communication, and we decided to try to design algorithms without these sensory modalities and abilities. That's why we are designing strictly decentralized systems that are scalable, that could allow us to design or deploy really large groups of robots. We are working in unknown environment. Of course, you can't map a single tree in all the trees in the forest, for example. And we are focused on flying in high density of obstacles because we are focused on multi-rotor drones, small helicopters, I would say, not on the fixed wing. Usually the large fixed wings are flying far from obstacles, but these small robots are able to fly even indoor, close to obstacles. That's why this motivation. We managed to get several achievements on this way. One of the most important, in my opinion, is onboard relative localization. Similar as you can see in the nature, like fish, birds, or even humans going in crowds, we have sensors to localize other entities around us. And also the robots, they have to perceive the other robots around. So this is, in my opinion, the fundamental, the key instrument to be able to achieve compact swarming. On that way, we tried to design many methods with different sensory modalities. We tried RGB cameras, 3D cameras, 3D LiDARs, RGB lights, April tags, whatever. We achieved a lot of really good publications with a lot of citations. Everything was great. But none of these systems is really working in all the conditions, in all the environments, in all the lights, visibility, and so on. So in fact, I cannot recommend them, unfortunately. But what we found the most working in most of the condition is a system we call UVDAR. It was designed by my PhD student, Victor Walter, and he proposed to use UV part of the spectrum of solar radiation because of the fact that this part, as you can see in that graph, is filtered out by the atmosphere. So if you use camera with a filter which allows to get on the chip only the UV part of the spectrum, you will get a black image. And you will see only the bright dots here, which are the LEDs mounted on the robot here. Based on this information, we are able to relatively localize the drones and also to communicate, because we can control the light of the UV markers. We can do some blinking. Currently, we are working even on a very fast sensor, which is using event-based cameras together with a group of Professor Matas. And we should be able to achieve really like almost optical communication, which is more reliable than the normal type of communication, mainly in large large teams and large swarms. The second kind of big achievement or tool we designed, which is kind of used by many researchers worldwide, is a system we called MRS UAV system. It's a control architecture which is used for all the vehicles we are using, all the swarms, even for boats and ground robots, but mostly for aerial robots and controlling of the robots. It is open source system. It contains several controllers, several sensors. We can even combine several sensor modalities together. There is a lot of planning approaches, localization, everything you need to be able to deploy a multi-UAV team in the real-world conditions. As you can read here, we counted more than 1,000 registered active users of that system worldwide, and this is a basement we are using in all our projects. So combining these two, let's say together, we were able to fly in the forest as I intended at the beginning of this research. But as you can see, the drones are relatively slow. This is the motivation of the Gacha projects of Robert Pieniczka to make it faster. So these experiments were done 7-8 years ago. It was the first deployment of fully decentralized multi-robot aerial team in such conditions worldwide. We manage also flying in demanding conditions of the desert. In these experiments, we found another interesting problem. If we are not relying on GPS and communication, it's without communication, without GPS, we can find some parts of the environment where the visual inertial odometry, which is used as a tool for localization of robots, has problems because of missing visual features. Imagine that we are flying above a flat terrain, flat sand, without any bush, as you can see here, then the robots are in trouble. So this motivated our further research, as you can see here. So this is let's say, the challenges we are working right now on. The agile flying, this I have mentioned already, also fast perception, fast relative localization, this is the event cameras, but also the navigation of the robot itself. If we are flying very fast close to obstacles, all the classical methods cannot be used. Then the long-range missions, let's say flying in huge maps, the Gacha of Tomáš Báča. And then the third part, which is my own research currently, is how to deal with the reliability or how to increase the reliability of GNSS denied localization, mainly in the parts of environment with degraded environment, let's say, where there is not enough features. And how to combine more sensors in multimodal perception, which is required for transition between different parts of the environments in the real world. So some almost randomly selected results in this way, which I found interesting. This slide is on the increasing of the reliability. If we are talking about fast swarming in plain GNSS denied environment, where you may find areas without sufficient number of, in this case, visual features. We have designed a method that can use the advantage of swarm and help the individuals that are in trouble. If you take a look on this experiment, there is only one robot which is, from this moment, using visual inertial odometry. None of the robots are using GPS, and there is no communication. The only source of information is the UVDAR, which is the relative localization between the robots. So without the swarm, the robots, without visual inertial odometry would crash in less than 3 seconds. But thanks to the fact that they are connected to the swarm, they are able to continue the mission. Because the one healthy robot, which has a working VIO, can even steer the swarm towards the intended position. So this is one of the first examples where the swarm can really help the individuals. Usually, the deploying of multi-robot system is decreasing the reliability because of increasing of the complexity. But here, we could show that the swarming can really help. And this example goes even beyond this. I'll stop it and before a little bit describe what's happening. So we have here 4 robots. None of them is using GPS. So there is no GPS being used. There is no communication. And even there is no localization, measuring of the velocity relatively to the ground. If you have a single vehicle, so imagine that this yellow guy is not connected to the blue guys. So this one is not equipped with the UV-DAR, which would see the other members. So you will see what will happen if a single vehicle is without kind of any source of information. It's completely blind. It's using only IMU, which is relatively cheap in our drones and which is very noisy with a drift. So if I will run the video, you will see that this yellow guy is crashing almost immediately, less than 3 seconds, as I said. And the blue guys, they are continue into a randomly, kind of not selected, but into a random direction, which is given by the drift of IMUs, which are combined on all the robots. So it is a very surprising result that even without this information, the swarm is more stable. We are now working on a publication in robotic science. These are some preliminary results of the event-based perception. As you can see here, the camera is so fast that we can see even the frequency of props. Again, with Professor Mata's group, we are now working on detection of these frequencies of props. And we could be able to detect not only the relative position of the robots, but even not only the velocity, but even the acceleration, or even derivative of acceleration, second derivative of acceleration. Because as you know, before the drone is starting acceleration, it must start like turning these props more than these. So if we are able to read the frequency of the props, we could detect that the drone is going to tilt and then going to accelerate. And this is probably the same behavior which is happening in swarms of birds and fish, which we are also trying to detect in the real nature in cooperation with biologists. So this second, let's say, work, I hope we can get into the big science, not only robotic science, but this is future work. Let me now spend the remaining 3-4 minutes with the key application focus projects, because as I have mentioned, we are not focused only on basic research projects, but for us also the applications are important. This has been already mentioned during the ceremony of Pavel Petráček. It's his project together with Vít Krátký. They were working on deploying of teams of robots for documentation of dark areas of large historical buildings. We have designed a formation of robots that are trying to realize this lightning techniques. It's called 3-point lightning. And in fact, we placed on some of the vehicles the lights, and some of the vehicles were equipped with the camera. And together they could control not only the field of view of the camera, but also the illumination in a smart way. So it was one of the first deployment of real closely cooperating formation in the real-world application. It worked very well. we managed to...
areas that are difficult to be accessed without a static infrastructure. We present
I don't want this sound, but
an area
I will stop
for
it anyway.
of historical monuments which cooperates fully autonomous drones in documentation.
Okay, perfect. So we could deploy that system fully autonomously in around 20 historical buildings in Czech Republic and Poland, including UNESCO heritage buildings, without any crash. There was only one small crash, but don't tell it to anybody. Another highlight I really like is a project Eagle One. It's a drone hunter. It's intended to be deployed to protect critical infrastructure like airports or even stadiums with people against non-authorized drones that could be potentially dangerous. The drone is already becoming a product of a Czech company, Eagle.1. The onboard AI is a result of work of two our PhD students. The drone is equipped, or my PhD students, the drone is equipped with the 3D LiDAR to detect the target, and it's capable of designing aggressive maneuvers to catch that target in real-world conditions. Another interesting project of deploying of multi-robot systems is a project that was led mainly by Tomáš Báča. It is on using a very small radiation detector to detect the sources of radiation. Thanks to the usage of a formation of robots that were cooperating together, it is the only system worldwide that is capable of detecting a moving source of radiation by aerial robots. Yes, so I did it perfectly on time. So I'm now getting into the second part of my presentations, which will be mainly about myself. So the purpose of this part is to show you my scientific and academic achievements and contributions to the university and to the, let's say, research community. We have a really good system at the Czech Technical University, which is combining all the results of all the members of the university. So I use this system because automatically it generates all the data. And even there is a nice functionality that you can get a ranking of all the researchers at the whole Czech Technical University. So let me press the button. I'm really proud to be considered like within the best of the researchers. Of course, we all know that there are some coefficients that are summing all the results together. Some of you and even me don't like some of the coefficients, so probably I shouldn't be the number one, but maybe somewhere lower. But I'm happy to be kind of evaluated as one of the good, and it's a good motivation for me to continue in this way. But let me go to details. Publications. Of course, I could try to impress you by number of citations, H-index, and by the curve of the citations. I'm also like proud of it, and I hope this curve will continue a little bit longer. But what I like more, or what is more important for me, is the quality of the results, not only the quantity, as could be in the other graphs. So that's why I prepared a slide about my results in M17 plus methodology. I'm proud that I asked our admins to give me some statistics, and I found that around 10% of results in the past 6 years are where I contributed. Even in this year, 3 of my results are nominated by our faculty. So I'm proud that I can help also the faculty in this way. Teaching. I successfully introduced a new course of multi-robot aerial systems. I'm happy that our students are enjoying the course. You can read the red parts I highlighted. What I like that the number of students is growing every year because like they know that they can get really good, let's say, knowledge there, and they enjoy the course. PhD students. I am really proud of my PhD students. So far, 8 defended. All of them with very excellent results. All of them received excellent reviews. In fact, all of them achieved some prize. You can see even Siemens, Fourier Prize, Antonín Svoboda Prize. Most of them are getting Dean's Prize. Some of them not because they did it a little bit longer, but they got also enough results. Now we have a little bit problem that a lot of students finished this year or the last year, so there will be some high competitions for the Siemens. So I will be surprised who will get it, if some of them. Other students are coming also soon, and they have also good results. Another highlight is the summer school we are organizing every year. As you can see, we attracted already more than 600 students from the most prestigious universities worldwide to Prague. Last year, I was asked by some journalists what technical universities are usually the students from, and we checked and found that there was 29 universities from the top 30 technical universities worldwide. So really everybody is coming, the biggest names. So I'm happy that we are able to get these people here and they can cooperate with our students. We also attracted more than 100 students from the Czech Technical University. They can enjoy really the best professors at the summer school. You can also see that on each of the pictures, I am carrying a small baby or my wife, and I have 5 babies. So we could have 1 baby per the summer school. Good news is that we are continuing organizing the summer school. There will be some more summer schools this year as well, but I hope there will be no more babies. So, projects. As I mentioned, I could kind of lead several gotcha projects. Now I'm working on the 4th one, or 5th one even. 5 gotcha projects, several toucher, European project, which was very successful at the end, one of the best robotic projects that year, Naki and some others. Industrial contracts, we have a lot of contracts with Czech companies, but also with companies from the rest of the Europe or world. I counted the income from all the HSky industrial contracts as 80 million Czech crowns for the university. There was also income from the prizes of the competitions, as you can see here. I put red the one I contributed a little bit more. The black are mainly thanks to Tomáš Svoboda, who led the team for the DARPA. Public relations, I asked our PR department to prepare, to count number of articles in the last year. My name appeared in 123 articles, and TVs, so it means every 3 days. Usually there is something happening. And I'm really happy to see that many of students are telling me that they selected to study here at our faculty because of drones and because of success in the competitions we had. So I'm also pushing this a lot because, in my opinion, it's helping not only me, but the whole faculty. Yes, this slide is mandatory. I have to keep it here, and we can start discussion. I have one minute more even.
Thank you very much for your very interesting lecture on your multi-robotic system groups and for detailed information on your scientific and academic achievements. Now I open the floor for the discussion and ask for questions. Professor Kittler.
Thank you very much for the presentation, fascinating talk. You had to solve many problems throughout your research. And I wondered which one was most challenging scientifically and what was unique about your solution.
As I have mentioned, we are known in our community mainly because of the ability of deployment of the system in real-world conditions. So when we started, it's like 10 years ago, there was like a lot of groups flying indoors. They were using motion capture system and everything was really like ideal conditions. But we decided, also when we started, we didn't have enough money to buy this expensive system, to say true. But we decided to go a different way and really to go to the nature. And we tackled a lot of problems there, even with the basic stabilization of the drones. We couldn't use the stuff which were being used by all the others. So we had to design a lot of from scratch. And it was really, that time, I was not sure if we are going the correct way. So like really, the first seat probably was the most difficult. Then, as the ball was rolling, it was maybe, I mean, more automatic to achieve some results. And now, as I have mentioned, for example, like this swarming without the VIO and without the localization is really unique. And even like, yeah, I didn't really expect it that it's possible, you know. So this is a nice result. I'm proud of.
Thank you.
Thank you.
Professor Železný. Just a moment, please, microphone.
So I understand your drones are deprived, or you assume them to be deprived of the localization signal, right?
Excuse me?
They do not. Your drones do not have access to localization signal from like GNSS or whatever.
In some projects they have.
But they still can
survive,
communicate between each other, and perhaps through a mobile connection to a server. Is that correct?
So if we are talking about the fundamental research, we are in most of the focus on deploying of robots without any global localization. So they have only onboard sensors, they can't use GPS, and they can't communicate. So there is no communication, no GPS, no server.
So my main point is, if they can communicate to a static server somewhere, what's the big deal about having all the AI on board? You made quite a point of it. But wouldn't it be smarter to have all the heavy AI computation, maybe including deep nets?
Sure. So if I would continue the answer, in the industrial projects or in like competitions, we are using all the resources we have. So usually the strategy is, if there is a communication, use the communication. If there is a cloud connectivity, use the cloud computation. But don't rely on it, because in many situations, and it was also in the DARPA, you know, sometimes there was connectivity. Use the connectivity, but be prepared on the situations when there is no connectivity. So this motivated the fundamental research. We wanted to design system which is using like really minimalistic information possible. So what is the research question was, what is the sensory information which is really the minimal I can use and still be stable and be able to cooperatively fly? So for example, that example where the robots are not having even visual inertial odometry, they were very blind, only could see each other. Of course, the performance of such a system is limited. Even we couldn't control the direction of the flight because we didn't know the velocity. But it survived and was working. So if I get question like, okay, if you can't control even the direction, what is good for it, right? The answer is, it is a backup mechanism. So imagine that there is some, and now we can see it in Ukraine, right? So if there is jamming of communication and GPS, we can at least survive and maybe get into an area which is more safe, where we can have visual features. So this can be the motivation of the fundamental research. Thank you.
Professor Kratochvíl.
I have noticed in your list the feedback from your students that one of the students is appreciating the system of homeworks. Homeworks from the lectures or from the how the system
from the practicals.
From
yes,
the practicals.
So we have practicals which are like there are some homeworks. Yes.
Is it mandatory or voluntary? Are there any extra points or points included in the evaluation? Are you evaluating these homeworks personally?
I have fortunately a team helping me here, so it's not only on my shoulders, but it's not mandatory. Nothing is mandatory, right? But it's included in if they want to have 100% of points, they have to do it. So the system is that there is like, let's say, 10 points per such homework, and if they are too late, for example, they'll get less points, or if the result is not perfect, they will get less points. But yeah, many of the students are really good and with perfect results. Like the advantage of the course of our course is that it's at the end of the studies, and it is non-mandatory, so they are really motivated. So that's why I really enjoy even the lectures. Thank you.
Maybe I would like to ask one question. Are there any difficult, harsh weather environmental conditions under which the stability of the drones fail? I mean, a very strong wind or a dense rain?
Like, of course, if the wind is stronger, faster than the maximum speed of the drone, we cannot fly, we cannot survive. If we don't have GPS and there is no visibility, maybe we can use radars. So always, or often, there is some sensory modality which we can use, but of course there are limits. For example, even if you are flying close to zero, there can be like some freezing of the props, you know, like in big airplanes, the same, right? So I remember, for example, what happened in this DARPA SubT challenge. At the first kind of trial, we are working with 2D LiDAR. And from some reason, this sensor was affected a lot by the dust. So we used 3D LiDARs and we were even playing with selecting the frequency, which is kind of penetrating through that particles of the dust from some reason. So sometimes you have to, that's why the sensor, the kind of fusing multiple sensors is important. Because sometimes, camera is good, but if there is fog around, you have to use LiDAR. But if you are far from obstacles, and the LiDARs have range 50, 100 meters, if there is a plane, you can't use your LiDAR, right?
Okay, thank you very much.
Thank you.
So, do we have any other questions? Seems not. So, thank you again to the presenter for impressive lecture and the audience for asking a question. I close this session, and the program of the Scientific Council will continue in a few minutes in the room number 80 in the ground floor, and I ask both committees and the presenter to join us.